Okay, so we're now going to look at the small amplitude disturbance. So this is it's not something that we're going to look at a lot because we're not really interested in it because it'll be linear. So if we assume the density is, this is linearizing, this is what happens with lots of problems, you can linearize them. So we assume that rho prime is small. So we're going to linearize, this is a linearized problem. I don't know whether linearized has a Z or an S. Okay, that's debatable. All right, so we've got d by dt of a rho is equal to d by d, that's right, plus c of rho d rho dx equals 0. So now we go the time derivative. This is the constant. Rho naught is small, is the constant. So the idea of linearization is really simple, right? You just differentiate here and you're going to get d by dt of this rho par plus, and then this is just c of rho naught, a constant. It doesn't vary enough compared with the variation here is going to be a small number times another small number. So it's going to be even smaller and disappear. D by dx of rho prime equals 0. I don't know how much detail to go into that, but the next term would be the term we're missing here. Perhaps it's useful to write it down. The next term would be c dashed of rho naught times rho bar times d by dx of rho bar. Okay, and so this is a small number times a small number, and it also makes it nonlinear. So if we just make rho bar bar even smaller, so that's small. Okay, it's a small times a small, so it disappears. So we end up with this equation here. So this is a constant. So this, you can see here now why it's speed here, because the solution is just simply, it's a first order wave equation, f of x minus c of rho naught t. So this is wave equation. So it's moving either to the left or the right. So it's the function depending on the sign of c of rho. So it's a traveling pulse. So linear disturbances of those small disturbances in the traffic, if the traffic's moving uniformly and there's tiny disturbances, they'll move with this speed given by this function here. And so it's either going to move forward or backwards depending on the density. So C of rho naught is greater than 0. Okay, so that means V naught is greater than V is greater than V naught over 2. Then the traffic will move, the wave moves to the right, the direction of travel. Okay, and that's the direction of the cars. Remember, this is a single road of cars. It's one lane of a motorway or 2 lanes of a motorway. It's not, you haven't got cars going both directions or anything like that. And they're always moving all the cars are driving to the right. Okay, and then if C naught, rho naught is less than 0, move to the left. I'm not going to say too much more about the linearization. Okay, maybe this final thing here that we talk about the characteristics, because they're going to become really important. The characteristics are x equals x naught plus c rho naught of t. Okay, so you imagine that they're all going to be straight lines. I draw a picture of the characteristics up here. Okay, to avoid using my special space. The characteristics are all straight lines. Nice and simple. Okay, couldn't be easier. Everything moves along those straight lines. They may be sloping that way or they may be going this way, depending on the density of the traffic. Okay, so the initial conditions, if there's a slight disturbance here, it'll be carried forward in one, carried backwards in another. All right, that's the linearized problem. We're not going to say too much about that. Now we're going to go and do the nonlinear problem.